Okay guys, I just want to remind you that where we're headed is this equation T1 plus plus sum of all the work from 1 to 2 is equal to T2. This equation, and we'll see this in 14.2, it's called the principle of work and energy. It allows us to solve problems involving force, velocity and displacement. Okay, but before we get there, we want to focus on this second term, which is the work of a force. Okay, so that's what we've been doing in the last few videos. So here is a nice example of how to solve or to add up to calculate all the work done on a particle due to all the forces. Okay, now let's have a look at this problem. We have this block, it's 10 kilograms. It rests on a smooth incline. If the spring is originally stretched 0.5 meters, determine the total work done by all the forces acting on the block. Look here, this is it. The total work done from state 1 to state 2 of all the forces acting on the block. Okay, so this is a nice example of how to calculate the second term. So determine the total work when a horizontal force of P equals 400 is applied and the block moves up the incline 2 meters, S equals 2. Okay, so now how are we going to do this? The first thing we need to do is we need to know that this is the sum of the work done by all the forces. The forces. Okay, that's not forces, that's forces. So what do you imagine would be the first step? The first step is to draw a free body diagram. That is amazing. Okay, so let's have a look. What are all the forces acting on this block as it moves up? Well, the one we know is this P equals 400. It's acting in a horizontal direction, negative X direction. Okay? The next is, as you're pushing it up, there's a spring force that is resisting the direction of motion. So you've got a spring force acting in the opposite direction to the motion. Then you've got weight, right? That's acting in the negative Y direction. And you've got this normal force. As this block is moving up, you've got this normal force. So you've got 1, 2, 3, 4 forces. 4 forces acting on this specific block, in this specific case. So we would now like to determine what is the work done by each force. And I just want to remind you, this is the most general equation, 14.1. It's the dot product, the integral of the dot product between the F and dr. Okay? So let's now look at what they do. We'll just follow them. The first is they look at this force of 400. Now my question to you is, if we look at this most general equation, is F a constant? Is this 400 a constant? Yes. Oh, so we bring this force out of the equation, out of the integral. Is the angle changing? We apply a force of 400, and as we apply this force of 400, this block moves up. The angle is not changing. So we will then use this equation. Constant force, constant angle between them, times the displacement, S2 minus S1. Okay? So that force is 400. Remember, you can either do F cos theta, displacement, or you can do F times S2 minus S1 cos theta. They're both the same. So the work done due to the constant horizontal force is 400 times 2 meters. That's right. Remember, I'm just going to draw it. There's the constant force vector. There's the displacement vector. Right? There's the constant force. There's the constant force. There's the displacement. There's the angle between it, between those two vectors. So 400 times the displacement times cos of that angle. Remember, work is only done if the displacement is in the same direction as the force, or if the displacement has a component in the same direction as the force, or if the force has a component in the same direction as the displacement. Okay, so 2 cos 30 and we get this. Or we can say 400 cos 30. Now we're looking at the component of the force in the direction of the displacement. It gives us the same answer. All right, great. So we've calculated the first one, horizontal force. The next one is the spring force. By the way, look at those two force vectors. Sorry, the force vector and the displacement vector. The components are going to be in the same direction, so that's why we have a positive work. Okay? Now let's look at the spring force. Let's erase this. The spring force is always acting in that direction. So, are we going to get negative or positive work? We should get negative work. The force is acting in that direction and the displacement is in the opposing direction. Okay, so we should get negative work. We should get negative work. Now let's go to the equation. We use equation 14.4, which is this, half k times s2 squared minus half k s1 squared. Now what is s1 and what is s2? S1 and S2 are simply the positions from equilibrium, right? It's the amount of stretch or compression at state 1 and state 2. So the spring was initially stretched half a meter. That's half a meter. So that was S1 equals half a meter. So that's why you have S1 here, 0.5 meters. And it was stretched 2 meters, so its final position is 2.5. Okay? So it started off by being stretched 0.5. You stretched it a further 2 meters, and that's why you get 2.5 here. Okay? So that S2 is 2.5, S1 is 0.5, and you carry it out and you get minus 90. That's exactly what we were expecting. We were expecting negative work. All right. Now let's look at weight. Okay? Okay, so the weight is acting down and this particle is moving up. Okay? So if you recall, because of the dot product, we only consider the vertical change because of this dot product. The weight is acting down and the displacement delta y is up. So we're going to get positive or negative work. We are going to get negative work for the weight, and it's going to equal the weight times whatever this component is, this 2 sine 30. Okay? So that's what we get. 98, that's the weight. And then we've got the displacement times the component. Okay? The component that's in the same direction, minus. So we get negative 98.1. Or we have the weight times the component times the displacement. We get 98.1. Negative work. Now, what do we want to do? We want to sum all of these up. So we add all of them up and we get, oh, I'm sorry, I forgot quite an important one. Our fourth force. So I've looked at these three. What about the normal force? Without looking, maybe you've already looked so you already know, but what does this normal force do work? Okay, remember, F dot dr. F is then the normal force dot dr. What are the directions of these two vectors? So the normal force is directed there, and the displacement vector is there. This is 90 degrees. And what is cos 90? It is 0. So if we have a force that's perpendicular to the displacement, then that force, the normal force, will do no work. And that's what we have there. This force does no work since it is always perpendicular. So what we do now is now we add up all the work due to all these forces. 692 minus 98 What am I missing? The first one. Oh, I'm missing this. Minus 90. 692.8 minus 90 minus 98. So that is the total work done by all the forces. Okay? So if this was part of a bigger problem, we could have this mv1 squared plus all the work done is equal to half mv2 squared. So for example, if we had the initial velocity of this block and we had all the forces and all this information, we could work out the final velocity, for example. Okay, but that we're going to do in the next section. Cheers.